You don't have a black marker up here, do you?
I got
Oh,
two.
He does. Do you want another?
I got a whole box. It's okay. Just keep
Jalen.
it.
You had all the chance to catch that.
You know what? I'm gonna leave this all in the video. This is great. This is gold. All right. Our objectives and our topic. Okay, we're gonna talk about properties of logarithms. We're gonna apply the product, quotient, and power properties. Okay. And if you know your rules of exponents, it kind of mimics some of that. Write a log expression in expanded form. So we're gonna have a log where it has a bunch of stuff in it. And we're gonna expand it out. Okay, and then we're gonna do the reverse. We're gonna have everything like expanded, and we're gonna make it into one log function. And then the last one, I'm gonna explain to you how you can change the base of a log, and it's still the same thing, which is really cool stuff. Okay, so here we go. Let's talk about some properties. First property. Product property of logs. Let B, X, and Y be positive real numbers where B can't be 1. Then log of base B, xy, is the same thing as log bx plus log by. So if you look at your argument, if you have two things being multiplied, in this case an x and y, it's the same thing as you splitting it up and adding them together. Okay, those are equivalent to each other. Okay? Don't believe it? Let's prove it. Let's prove that, okay? Now, here's the deal. You guys, in your homework for tonight, I think there's one or two properties you're gonna try and prove for me. And it's gonna follow this format. It's very similar to it, okay? So let's go ahead and see if we can't prove that that's a true relationship. So, here's the proof. So let's define some variables. Let B, X, and Y be positive real numbers where B can't be 1. We want to show that this relationship is true. Okay? Anytime you start a proof, you gotta have like, what are your initial conditions to the proof, right? So again, B, X, and Y, positive real numbers, B can't be 1. We want to show that that is actually a true statement. Okay. Now, what I'm going to do is clean this up a little bit because there's a lot going on here. So I'm going to define some variables that's going to represent some of these terms. That way it's easier to manipulate. So let's let the variable P equals log B of the X, okay, and R equals log B to the Y. Okay? So I'm going to replace the right-hand side with the variables P and R. Okay? Let me make that Y a little bit better. There we go. Okay? Now, using the exponential form of each log, we have, okay, so what I'm going to do, if you look at my variables I defined, I'm going to rewrite this in its exponential form, and this guy in its exponential form. Okay, so here's what it's going to look like then. So we're going to have b raised to the p power equals x, and b to the r equals y. So let me just use another color. So right here, okay, I rewrote those in their exponential forms. Okay? So then, now look at the property. You see on the left-hand side, they show me multiplying those together. So let's multiply these guys together. So then xy, this is just about done, so. Okay. Then xy is equal to b to the p power plus, or not plus, times b to the r power, okay? So again, I just took my exponentials, multiplied together, and I get this as a result. Okay. Now if you remember your rules of exponents, same basis, you add the exponent, so b to the p plus r. So this guy, if you multiply x and y together, that's going to be your answer. Okay. Now, let's write this in logarithmic form now. Okay. So, here we go. Writing xy equals this in log form, okay, we have log, okay, base b to the xy equals p plus r. So again, I'm just going in the reverse direction. So at the very beginning of the proof, I changed these logs to their exponentials. And then I got this as a result when I multiplied them. Now I'm going to change this into its log equivalent. So remember, when you do that, this is going to be your base. That's your argument. And then the power is what the log is equal to. So now for my last step, because this doesn't quite look like my property, but remember, P and R represent something. What's in those purple boxes? So therefore, log base b to the xy is equal to what we wanted. So this is just me substituting what P and R are. There we go. So yeah, if you multiply, if you have an argument with things being multiplied together, it is equivalent as if you split it apart and add the logs together. But hey, that's pretty cool. It's a nice little property there. Let's use it. Now that we know that it works, we proved that it works, let's start using it. So let's see, example. Write the log as a sum and simplify if possible. And that's always something you want to consider. Like when you actually break it into one or multiple logs, simplify as far as you can. Okay? So yeah, we're going to have two little examples here. So A's example will just be log base 3, 27x, and B's example would be the natural log of x squared times y cubed. Okay? And again, I'm not trying to solve anything, I'm just trying to break it apart. Okay? So I'm going to break these guys apart using this guy right here, using that property. Okay? So I'm just going to pause for a small bit. Do we have questions so far? Okay, let's use it. So for part A, look at the argument. You got a 27 and x, right? So what two things am I multiplying together? 27 and x, right? Okay, so let's use it. So this is going to equal, and I'll tell you what, just to make it pop, let's use a different color. Okay, so this is going to be log base 3 to the 27 plus log base 3 with the ends. Okay? Actually, wait a minute, we can't simplify that further. Oh, I jumped the gun. Let's try that again. So there it is. Actually, since I just said it, do you see which one simplifies? It's this guy, right? 3 to what power gives me 27? 3. So this simplifies to just 3 plus log base 3x. So there we go. So there is an advantage of splitting it apart. There could be things we could simplify with that. Now this guy, just because it's a natural log doesn't mean the rule doesn't apply. It still does. Okay? So this is going to equal ln x squared plus ln cubed. And we're done. I don't know why I did that. I boxed that one. Why didn't I box this one? I don't know. I'm trying to be consistent. Okay. Any questions? So far, so good. Okay, that's the product property. So now let's talk about the quotient. See if I can, there we go. Quotient property of logs. Let b, x, and y be positive real numbers, where b can be 1. Then log base b for x divided by y is the same thing as if you're subtracting. So I'll put a little purple box around that. So there's my next property. Okay, I'm going to put here the proof follows the same process as before. Okay, and it's left as a homework problem for you. Okay, and tomorrow, I don't know, we'll see if someone wants to put it up here afterwards. So tomorrow we'll take a look. But yeah, it's going to follow the same process. Okay, so if you look at what we just did prior, follow that through, and see if you can't come up with this property. Okay. So let's try an example underneath. So write the log as a difference of logs and simplify if possible, because you might not be able to. Okay. I have 2 examples here. Those 2 we're going to tackle. Just trying to space out a little bit because today's lesson's not too lengthy, but I want to make sure we're not losing anything here. So for part A, okay, using the property, it's the same thing as me splitting up the argument, right? Notice that the numerator is first when you're writing this down. And the bases stay the same. So it'll be log base for A minus log base for B. And I don't know what A and B are, so I can't simplify any further. We're done. Once you tell me what A and B are, well, then we could, but I can't. Natural log still follows the same process. Okay, just because these are just saying logs doesn't mean natural log doesn't follow it. It does. So we'll put equals here. So we'll have ln, natural log of 5 minus the natural log of e. Now we can simplify something in this one, right? It's this guy. Okay. What's the natural log of e? 1. It's 1. Okay. And then that's our final answer. Because remember, I don't write, the base is e here, right? We don't write it, but the base is e. So e to what power gives me e? 1. That's what that is. Okay, that's 2 properties down. Any questions on those 2? Doing good? Now I want you to think about something for a moment. Think about your exponentials. When you multiply 2 bases together, don't you add the exponents, right? See how that kind of follows it? When you're dividing by 2 like bases, you subtract the exponents, right? Well, that's what this is doing. So again, if you really know your properties of exponents, logs are following them, which is really cool. Okay, let's talk about the last property. And this one's also left as a small little homework problem for you to try and prove this one, okay? This is going to be the power property of logs. Never gonna guess what I'm gonna write down. Let b, x, and y be positive real numbers. And guess what b can't be?
1.
That's right. Paying attention. Okay. Let p be any real number. Then log base b, the x raised to the p power, is the same thing as you bringing the power out in front of it. Okay? So if you have an argument with an exponent, whatever that exponent is, you can bring it out in front. Okay? And it's equivalent to what it is originally. So like I said, that one you're going to prove as well, but I'm going to give you a little hint to help you with it. Okay? So I'm going to put here hint to prove. Start by letting m equal log base b to the x, then b to the m equals x. Now raise each side to the p powered. So there's my hint for you. So to start, in this case, just let a variable, like in this case, m. Okay? I can't use p like I did before because p's in the property. That would be very confusing. So m just equals this. Write it in its exponential form, and then raise each one to the p power, and go from there. Okay? So let's use it. There we go. Well, this one has a difference. It just says apply the power property of logs. And I got two examples here. Okay. So for part A, notice that the argument's being raised to what, the 100th power? So using this property, all I gotta do is bring the 100th power out in front. Okay, so this is gonna equal 1,000, no, not 1,000, 100, huh? Sorry. 100 log, now this is a base 10, right? Even though we don't write it, so just keep that in mind, to the x, okay? Now, one thing to note, this is where x has to be greater than 0, right? Because remember, domain-wise, we can't let that be negative. So there's my final answer. That's it, just bring the power out in front. Natural log still follows the same suit, but notice it doesn't look like there's a power there immediately, right? But there is a power there. That's a square root. What's the exponent for a square root? What half? It's a half, right? So it does have a power there, it's just not written. So here's what we're gonna do first. Okay, let's rewrite this. So this is ln, so this whole thing will be x to the 3/2 power. So just a little quick refresher. The bottom of the denominator tells you what root. The numerator tells you if there's a power underneath it, and there was a 3. Now we're just gonna bring the 3 halves out, and there's my final answer. Okay, any questions on that? And I should put there, just like that one, okay, so this is where x is still greater than 0, okay. The reason why I didn't write it in the other ones is because it was already assumed to be that, okay. So from here on out, I'd say let's just assume they're always positive, so that we don't have to worry about writing that every single time. Okay, those are the properties. So now let's see if we can't expand some of these next laws, okay? So let's look at some examples here. Let's try expanding some things. I would recommend, as you guys are practicing this tonight, okay? Maybe on a separate sheet of paper, write the properties down. That way you have it next to you so you're looking at it through each example. Just a thought, might help. So now let's write log expressions in expanded form. Now the reason why we do this, and you kind of saw a little bit of it in some of these examples, some things can reduce, right? Okay, and that's a possibility. So expanding it has its benefits. So our first example, write the expression as a sum or difference of logs. I don't know if that's a square. Okay, so those are going to be our two examples. And you want to take your time with these, okay? Because here's the deal, when you're done at the very end, you want to check it by saying, okay, is there a property I didn't use? Is there something else I can, expand further? So looking at part A, the biggest thing that I see is the fraction, right? Okay, so if we're dividing, then that means we're doing this, huh? We're subtracting it, right? So let's start with that first. Because right now you're probably thinking there's a lot going on there, but you can only tackle one thing at a time. So this is going to equal log 3z minus log base 3 2x squared. Okay, so let's just take care of the fraction first. So we know that that is the same thing as subtraction. Okay, next, let's start looking at each individual log to see if there's something we can't break down. So for the first one, is there anything here I can break down with it? No, there's nothing extra. This guy has a lot of extra, right? Notice there's some multiplication going on, right? So let's split that apart. So if we're multiplying things, isn't that the same as addition, right? So let's go ahead and tackle that. So minus, and I'm going to put this in parentheses because we're subtracting this thing, right? So I'm going to break this apart using the product rule. Okay, so I broke up the 3, oh not 3, the 2 and the x squared. Okay. Alrighty. Now, again, go back through each individual one. We know that's simplified. Is that now simplified? Yeah, right? Okay, there's no exponent raised to 3 that gives you a 2. We're getting there, by the way. I will show you how to find that, but right now we have no nice value for that. And then over here, my argument has a power, huh? So one of the rules we just said was the power of that argument can be brought out in front. Okay, so let's go ahead and do that next. So log 3z. Now I'm going to go ahead and just distribute the negative so I don't have to worry about the parentheses. So I'll do that in this step as well. So minus log base 3, 2, minus log, oh, not minus log, minus 2 log base 3 nx. And now we're done. Okay. So that's it fully expanded. Now, did we really break it down any further? Like, were there any things they were able to simplify? Not exactly. And that happens sometimes, okay? But I don't know what context this is from, so maybe that did make it simpler. I don't know yet. Okay, now this guy. A lot going on here again, right? But notice I can't break this apart yet until that power's taken care of, right? So what's the cubic root as a power?
1/3.
1/3, right? Yeah. Okay, so I'm going to rewrite this. So equals log 10. Okay, so I'm going to raise it to the 3rd power. And then we know that that's the same thing as me writing it out in front. Okay, so there we go. Now, could you do that all in one step? Absolutely. I'm just showing you, why did we get to a 3rd? Because that actually is an exponent to the 3rd. Okay, now look at the argument. What's the next big thing that we see there? It looks like division, right? Okay, so we know division means you're going to subtract the numerator's argument with the denominator. So let's do that next. Okay, so equals. Now I have to be careful. See how that 1/3 still lingering there? So it's 1/3 times me breaking this apart. So it's gonna be log base 10 2x minus log base 10 3x squared plus 1. Okay? And here's the, just to put it out there, when you have an expression like a polynomial as an argument, it's sometimes seen as they'll put parentheses around it just to make sure you know that goes to that log. So if you see parentheses around an argument, that's why. Okay, I'm almost done here actually. Can I break that apart any further? Not really, right? There's no rule, because there's a plus sign there, right? If this was just, if I got rid of this, if it was just 3x squared, I can go further with it, but I can't. So that's done. But this 2x, can I break that apart? Addition, right? 2 plus x, right? So let's do that next. So we get 1/3, and it'll be log base 10 2 plus log base 10x minus log base 10 3x squared plus 1. Okay, so I use the product property for that one. All right, and I think we're just about there, huh? I'm gonna go ahead and multiply the, well, I guess we don't really need to. It's not gonna break it down any further, huh? Be multiplied by 1/3 through everything. So we can leave it like that, but I'll tell you what, I'll put or underneath it. You can multiply the 1/3 through. Because sometimes it will help reduce things. In this case, it didn't. So if you want to multiply the 1/3 through, you can. Okay, but in this case, like I said, didn't really help us reduce. This can be a lot, because there's a lot of properties, right? So again, just take your time with it. Maybe your first try is gonna be correct, that's okay. Just go back to the drawing board again, like redo the problem, but always tackle what's like, it's almost like that Russian doll thing, like always tackle the outside stuff and then kind of work your way inside of it. Okay, you guys are doing good. Now, let's go the reverse direction. So this is expanding it. Can we take this and then put it in one form? Let's go the other direction. Okay. So make sure I didn't skip anything. No, I didn't. Okay. All right, so this is going to be, we're going to write log expressions as a single log. I might be able to. You know what? I might put the other example on that board. I don't want to squish things. So we'll start with this example, and I got one more after this we'll take a look at. Okay. Now, immediately, we see subtraction signs, right? So that's telling me division, right? Remember how subtraction and division are hand in hand? So we're going to have some division here. But with 3 of those, that's kind of tricky. So what should we do? Okay, and here's my suggestion. I'm going to take this guy right here, okay? And I'm going to combine those terms together, okay? And then once those are combined, then I'll incorporate the 189. Because again, to do all 3 at once, there's too much going on. So let me show you what this is going to look like. So the first term, I'm not doing nothing with. Now, I'm going to do something crafty. If I take a negative out of both of these, I get log 2 base 2 3 plus log base 2 7. So by taking a negative out of these terms, this became a positive for both of them. And because it's a plus sign, that's what the product property. I can now multiply them together. See how that kind of worked out nicely? And put it this way, when I first did this myself, that didn't come clear to me. You know, like I was going through my head and I had a couple little ideas down, and then it dawned on me like, oh, I could do something like that. So again, I don't want you to get frustrated if the first attempt you do, it doesn't quite work out. Okay, so log 2, 189 minus, so this is going to be log 2, this will be 3 times 7. Okay. Now, and I'll tell you what, just for an extra step, you don't have to do this, but I'm going to go ahead and just make that a 21. So I just but I just simplified that part. And just like we said at the very beginning, because these are subtractions, we know that's a division problem. So this is just going to end up being log 2, 189 over 21. Okay, which is log 2 to the 9 when you divide those guys together. I can't go any further with that because there's no power of 2 that gives me 9. Okay, so that's it. That's my final answer. Any questions on that? So far, so good? Okay, so when you get extended, like 3, 4, 5 log terms in a row, just focus on a couple of them at a time, not the whole thing. So that could be overwhelming. All right, let's try one with a natural log. The good news is the natural log follows the same process, but still, I want you to have one of these in your notes to reference. So this is part B. Okay. Actually, I kind of like using natural log because to me, that's one less letter. Which isn't a big deal, but it's a little bit speedier. Just a little bit. Okay. Now, a lot going on here so far, right? Okay. Here's what I would recommend. Because those plus signs tell me I'm going to do what to all those? Multiply, right? Okay, so it tells me that. But do you see how you have a 2 on the outside and a 4 on the outside? So weren't those originally powers when you bring it down? So maybe let's rewrite those as powers, and then we'll multiply them all 3 together. Sound like a plan? That way it's a little bit easier. So that's what I'm going to do. I'm going to underline this. So I'm going to use the property power, or the power, it's a power thing. We're going to use that. So ln x squared minus 9 plus ln. Now, 1 squared is 1, so I'll just put this 1 over x plus 3 squared. Okay? Just make it a little bit better that way. And then plus ln of x to the 4th. Okay. Now I'm going to use the product property for that one. Now that the exponents are all taken care of. So this whole thing is going to be ln. I'm going to put brackets around it because there's a little bit inside of here. So it'll be x squared minus 9 times 1 over x plus 3 squared times x to the 4th. Okay? Now, you might ask yourself, why didn't I do that with that guy over there? Well, with three values for division, that doesn't quite work nicely out. With multiplication, it doesn't matter. You know, you can multiply all 3 terms together. Now, what should we do next? Well, here's what I'm thinking. That x squared minus 9, do you think that's factorable? Kind of is, right? Because the first and last numbers are perfect squares. And there's no middle term. So it's the same factor twice, but just plus and minus. Okay, so what I'm thinking is we're going to do this. I'm going to underline that part. So I'm going to factor that out, and then I'm going to multiply all 3 together. So this is just going to be x plus 3, x minus 3, times x to the 4th, over x plus 3 squared. So I did 2 things in that step. I factored this guy out, and then I multiplied them all together. Okay? Now we can see some cancellation, huh? Okay? I shouldn't say cancellation, but reducing, right? We can see some reducing opportunities. So this will cancel out with just one of those guys, right? Okay? Which, hey, that's better than nothing. I think we should take it. So this is equal to ln of x minus 3 times x to the 4th over x plus 3. Okay. Now, here's the deal. You can leave it like that, or could you multiply the numerator and finish it? You could. I'll put that underneath here. So if you really want to finish this out, it'd be x to the 5th minus 3x to the 4th over x plus 3. And there we go. There's my final answer. All right, guys. We're doing pretty good. Any questions on that? Okay. Let's continue. So we're still going to apply properties of logs in this example, okay? But I'm going to try something different with you. So given that log base b2 is approximately 0.356, and log base b with 3 is approximately 0.565, approximate the value of log base b12. So here's the interesting part. I'm giving you some information. The b part could be any base, but the argument of 2 with it gives me an answer of 0.356. And then over here, it's the same base, but if the argument was 3, this simplifies to 0.565. So can we use other logs to approximate something like this? Okay, so we're gonna give that a shot. And we're gonna use some properties that we just discussed to do that. So let me rewrite the log part. So log b12, okay? Now notice, I'm not multiplying by anything. I'm not dividing by anything. So how can I break that apart? Well, if we have 2 and 3 here, maybe we can use those to help us break it apart. What are 2 factors of 12?
6 and 2.
6 and 2 works.
4 and 3.
4 and 3 works, right? I'm kind of more inclined to do 4 and 3. So let's do that. So this is equal to log base b, 4 times 3. Okay. Now that we're multiplying, we can use the addition property of it, right? So this is the same thing as log b, 4, plus log b, 3. A little crafty. Now, this guy, I know what it's equal to, right? 0.565. That guy, I don't. So what do? Well, can I break this down to where it has a 2? I think we can, huh? So let's do that next. So log b 2 squared, we can do, right? 2 squared gives me 4. Now that I have an exponent there, we have to use the rule. So you're going to bring the 2 out in front. And I think I have all my information now, huh? So this guy we know is 0.356. This guy is 0.565. Now I can plug those values in. Whatever my answer is, that's what's going to approximate to. And again, I don't know what base b is yet. I'm just making it any base I want. So over here, so this is going to be approximately 2 times 0.356 plus the other one, 0.565. And we get 1.277. That's my final answer. Okay. So given like other logs, we can approximate a log that we don't know, which is pretty cool. Okay. Alrighty. So the last thing we're going to do is the change of base formula. Okay, let me show you what that looks like. And this is amazing. Let me put this down here. Change of base formula. Okay. Let A and B be positive real numbers such that A can't be 1 and B can't be 1. Then for any positive real number x, we have the following. also put the natural log version of it too. Okay? So if I have a log with a base that isn't quite working for me, that sounds like a really bad way to describe it, but let's say I have a log base 2 and I want it to change it to a log base 10 where it's easier to work with. I can use these formulas here to change that base, okay? Now, let me just put a little note here. A is usually base 10, okay? So usually a base 10 is what we have for A. So if I have a base 2 log, I can change it to a base 10 log. And look at some patterns here, because a lot of times you look at formulas like, how am I gonna like memorize this? So it's the argument is always in the numerator, okay? And then whatever the base is for the original, that's gonna be the argument for the log in the denominator, okay? So it's always gonna work out that way. Okay? Now here's what I'm gonna do. I'm gonna show you an example underneath it. And, well, before I do that, over here it's the same thing. Sorry, I forgot to explain this. So again, the argument of this is going to be the numerator, just with a natural log with the base e this time, and then same thing in the denominator. You use the base for it, okay? So what I'm going to do is underneath it, I'm going to show you an example of showing you why that works. So that way it's not just me randomly giving you a formula like, hey, use this. Trust me, it works. So let's take a look at that. Actually, let me use this whiteboard over here. I don't want to squish that down there. Okay. So just to kind of flush this out. So let's express log base 2, 5 in terms of base 10 logs, okay? And by the way, if you look at the formula, they are equivalent to each other. So it's not like I'm just changing the base and it's not being the same number. It is the same number, okay? So let's let z be log base 2 to the 5th. So let's just give it equal to some number. I don't know what log base 2 to the 5th is. It's some decimal, okay? But let's just let it equal to z, okay? The exponential form of the equation, oops, out of space, is 2 to the z equals 5. Just using stuff we did in the past. Okay, so I took this expression, this log, and transformed it into its exponential. Okay. Now what I can do now is take the log base 10 to both sides. Okay. So I'm going to put that over here as a step. So I'm going to take, okay, base 10 log to each side. It's like me multiplying both sides by 10 or multiplying both sides by 20 or, you know, doing the same to both sides. So this is going to be log 10 of the argument 2 raised to the 5th power. Okay. Oh, not 5th, z. Sorry, that's a z there. And then on this side, log base 10, argument 5. So again, I just took log base 10 to both sides of the equation. Kind of like, you know, you're solving the equation here. Okay. Now using the power property, I can bring z out in front, right? So let's put z here. And then log base 10 2 equals log base 10 5. That's just me using the power property. And then I think we're about done. To solve for z, would we divide both sides by log 10? With this. So we'll divide both sides by this guy. So z is log base 10 5 over log base 10 2. Now here's the cool part. What was z originally? This guy. So let me just plug that in so you can actually see what it looks like at the very end. So this is me plugging z in. So it'd be log base 2/5 is the same thing as me saying log base 10/5 over log base 10/2. So there it is. And if you compare formulas, that's what this says up here. So it's not just like a random formula. You can do this, okay? If you wanted the base not to be 10, if you wanted the base to be 5s, you would repeat the process for 5, right? Okay? So any questions on that? So that's just me showing you that this works, okay? We can do this. Now, do you have to do that process every single time? No, you can just use the formula right off the bat. But I just wanted to show you, like, where does it come from? It can be done. Okay, so let's do that now. That's our last example, actually. Yeah, let's estimate a log using this base 10 or change the base formula. Here we go, guys. So example. So part A, just estimate log base 329 between two spelling consecutive integers. Okay, we're gonna use a little estimation here, and then at the end we're gonna check to see if we're close to it. Okay, so let's think about 29 for a second. So 3 to what power? I'm going to do that to both sides, by the way. I'm going to put 29 here in the center. So 3 to what power would be less than 29? 3, right? Because that's 27. Does that make sense? Okay, so over here we're going to have 27. And 3 to what power would be greater than 29?
The fourth.
Fourth, which is 81. Okay, so that's how I got to those values. Now this trick over here, remember how I took log base 10 to both sides? Okay, so I'm going to take log base 3 to both sides. Okay, so let me rewrite this, and they're exponential, okay? That way we can see, so that's 3 to the third, 3 to the fourth. Then take log base 3 to both sides. So we get 3 is less than log base 329, less than 4. So I'm going to put over here what I just did, because it looks like magic happened. So on this side I'll say take log base 3 to each part. Okay? And when I do that, the power property says that, you know, this just goes to 3 and this will just go to 4. So my log base 3 to 29 is between 3 and 4. So that's what we know. So this is going to help us a little bit to estimate. Okay, so part B says this. Use the Cobb formula. I abbreviated. Change of base. We're going to call it Cobb. Cobb formula to approximate log base 329 by using base 10 and E. Okay, we're gonna do both. I kind of want to keep the formulas up here, so I'm just gonna finish the problem right here underneath it, okay? So again, I'm just writing underneath here so we can still see those. I was kind of cheating. I didn't want to write change of base. So, Cobb's good. Cobb's good enough. Okay, let's look at the base 10. Okay, let's see if we can't convert it. So log base 329. So I'm using this guy up there, this formula. Okay, so this is going to be log, and the argument is in the numerator, and then log, and then what the base was here is in the denominator. If you want to write 10, you can, but remember, if we don't write 10, we already assume that it's going to be that. Plug that in your calculator, and we get 3.0650. Okay? Is that between 3 and 4? I think it is, huh? We did pretty good. Now, let's do it with a base of E. So we're going to use this formula over here. So it follows the same process, just change logs to natural logs. So log 3 to 29 ln of 29 over ln of 3. And here's the really cool part. It comes out to be the same answer. So it looks like log base 3 to the 29th is between 3 and 4, and specifically it's 3.0650. Okay. Oh, we could check. Let me just put it down here. If you want to check, okay, take 3, raise it to our power, and you get approximately 28.99, which is approximately 29, which isn't that what it said there? The argument was 29. So if you want to check, you could just use the base with the exponent you just found, and plug it into the calculator.